Hello and welcome to the last geometry lesson by eMath Instruction. My name is Kirk Weiler and today we're doing Unit 10, Lesson 13 on geometric modeling. This is the last video in our geometry series, even if you're not watching it last, which I could see for many of you. But Unit 10 is our final unit and Lesson 13 is our final lesson in our final unit. So let's get right into it and use a bunch of what we've learned in this unit to model a variety of real-world scenarios. Here we go. All right, modeling a solid with geometric shapes. Now, as we have seen in many lessons so far, both two-dimensional and three-dimensional geometric objects can be used to model a variety of real-world situations. In this lesson, we will work with choosing which solids to use. All right, so let's take a look at exercise number 1. James is designing a monument made from granite that weighs 44 grams per cubic inch. Notice that density in there. His design has a square base with a lower portion and upper portion as shown in the diagram. The total weight of the monument cannot exceed 80 pounds. Letter A. What geometric solids should be used to model the monument? All right, so again, we've got this total monument. We know a bunch of things about it. It's got a square base. It's got this upper portion, right? We know it's made out of granite that weighs 44 grams per cubic inch. That's a density right there. None of that matters for letter A. I just want you to tell me what geometric solids should be used to model the monument. Well, it's a prism and it's a pyramid, right? So the lower portion is a square prism, and the upper portion is a pyramid. But we're just going to say a prism and a pyramid. All right, so a prism and a pyramid. Simple enough, right? And clearly that's the case here. All right, now let's take a look at letter B. If there are 454 grams in a pound, how much does the lower portion of the monument weigh? Round to the nearest tenth of a pound. So I want to know how much the bottom portion, right, the prism portion of this thing weighs to the nearest tenth of a pound. What I know, right, is I know that it's got a density of 44 grams per cubic inch, right? So I should be able to figure out how many pounds that thing weighs. Pause the video now and see if you can figure that out. All right, well, the first thing let's do is let's just figure out what its volume is, right? Now, the volume of the prism is going to be the area of the base, which is 12 inches by 12 inches, times the height, which is 4 inches. So let's just come up with the volume of the base. All right, we've got 12 times 12 times 4. All right, and that's going to be 576 cubic inches. Okay, great. So we know what the volume is, 576 cubic inches. We also know that the granite that we're using weighs 44 grams per cubic inch. So each one of those 576 cubic inches is going to give us another 44 grams. So let's figure out the weight now in grams. So the weight in grams is 576 cubic inches. Whoops, times 44 grams per cubic inch. And let's see, I can just take that volume right there, multiply by 44, and I'm going to get 25,344 grams. Okay. So I know what my weight is in terms of grams, and yes, I know there's some people out there objecting right now and saying, well, grams are mass, not weight. Well, okay, go into the grocery store and complain to them when they sell you something by the gram. Okay, I'm sure they're going to call that a weight. Anyway, so we got 454 grams per pound. So if I want to turn that into pounds, then I will literally just multiply by 1 pound over 454 grams. In other words, right, I want to divide by 454 to figure out my weight in pounds, right? Divided by 454, and that's going to be 55.8 pounds. All right, So not too bad, 55.8 pounds, a little bit heavy, right? I wouldn't want to be lugging this thing around a lot, but there we have it. Now, by the way, remember from up here, right, the weight of the monument cannot exceed 80 pounds, right? It's got to be less than or equal to 88 pounds, or sorry, 80 pounds, not 88, 80. So now let's take a look at letter C. James has not yet decided on the height of the upper portion of the monument. Given your answer to B, what is the maximum volume in cubic centimeters that the top of the monument can be? Round to the nearest cubic inch. Okay, so now we almost have to work our way backwards, right? So before, we had a volume and we worked our way up to its weight in pounds. Now we really want to figure out what the weight in pounds can be of the upper portion and work our way backwards to try to figure out the volume in terms of cubic inches. Pause the video. This is going to take a little bit of work, but I'm sure you can do it. You almost want to go backwards from what we just did in letter B. All right, well, let's first figure out the maximum weight that the upper portion can be. All right, so our maximum weight, the max weight is going to be 80 minus 55.8. Let's just figure out what that is. All right, 80 minus 55.8 is going to give us 24.2 pounds. All right, so the heaviest that upper portion can weigh is 24.2 pounds. But I really need to get it in terms of grams, right? Because I know the density of the granite in grams, not in pounds. So that's easy enough. Let's get the weight in grams, which is going to be 24.2 pounds times 454 grams per pound. And that is now going to be, let me just take that and multiply by 454. So we are going to have 10,986.8 grams. All right. Sorry, just barely fit it in there. So a lot of grams. The gram is a very small weight measurement, right? 10,986.8 grams. Now, we know that we have 44 grams per cubic inch, so I can now take my weight and divide it by my density to figure out my volume. So remember, volume now is mass divided by density, and this really is a mass. And now people are like, why'd you call it a mass now? 10,986.8 grams divided by 44 grams per cubic centimeter. So we're just going to take this and divide it by 44. And we're going to find that that could be 249.7. And what do we want? Round to the nearest cubic inch. It really should say cubic centimeter. My apologies to the nearest cubic centimeter. No, it's cubic inch, not cubic centimeter. Wait a second, what's going on here? No, it's cubic inch. That was my mistake. I shouldn't have had centimeters here. Those are inches cubed there. So 249.9, and it says to the nearest cubic inch, so that's going to be 250 cubic inches. Oy, okay. Sorry, I'm so used to things being in cubic centimeters, not cubic inches, because most densities are in terms of a cubic centimeter, not in terms of a cubic inch, but here we're working with the English units. So the maximum volume that the pyramid portion can have is 250 cubic inches. Awesome. Got all my units right now. All right, so now let's take a look at letter D, right? We got to design this thing, and we're missing an important piece. Letter D. Determine to the nearest tenth of an inch the maximum height of the upper portion of the monument so that it does not exceed the weight limit. Awesome. Well, this, right, is the maximum volume we can have. See if you can use that to figure out what the height of the pyramid portion can be. All right, well, let's first talk about what the volume of the pyramid is, right? The volume of the pyramid is going to be 1/3 times its base area times its height, right? That's going to be the volume of the pyramid, okay? Now, the base area is simple because that is simply that square, right? That 12 by 12 square. So that's going to be 1/3 times 12 times 12 times h. All right? Now, to make life easy, it would actually be kind of helpful to just figure out what all of that is equal to. Now, 1/3 times 12 is the same as 4 times 12, which is 48. So the volume of the pyramid is simply 48 times its height. And now, because I know the volume is 250 cubic inches, I can now say 48 times the height is equal to 250. Divide both sides by 48, and we can figure out what the height is. We want that to the nearest tenth of an inch. So 250 divided by 48 is 5.2 inches. Excellent. 5.2 inches is the tallest we can make the pyramid portion of this monument and still stay within that 80 pounds. Let's take a look at one last little piece of this before we go on to our next modeling problem. This one's really quite cool. Letter E. There will be writing on the triangular faces of the upper portion of the monument. What is the area of just one of these triangular faces? Round your answer to the nearest tenth of a square inch. Ooh, boy. Now let's see what we know about these triangular faces. They're all identical, right? They're all isosceles. And what do they look like? Well, they look like this. And the only thing I know is that that's 12. That's all I know, right? What I don't know is I don't know the height. I also don't know any angle. I don't know the isosceles triangle leg lengths. I don't know that, right? But boy, if I want to figure out what this area is, it would be very helpful to have this height, okay? Now, keep in mind what we do know, okay? We do know that this height now is 5.2 inches, all right? But I hope everyone is aware, right, that the height that I'm talking about is this distance, right? And that distance and that 5.2, those are not the same length, all right? So I'd like you to pause the video right now and see if you can think of any way that I could figure out what this value is. One might call this a slant height, right? That height. Figure that out. Pause the video now and see if you can determine what that height is. Well, here's the real key, right? If I connect these two with a line like that, that is a right triangle, right? And I know everything I need to know about that right triangle, right? That right triangle looks a little bit like this. This is 5.2. This is equal to 6. And that's equal to that height that I desperately need to calculate the area, right? Now, how do I figure that height out? Well, that's where our friend the Pythagorean theorem comes in, right? And specifically, the interesting thing is that thing now is the hypotenuse, right? So I'm going to say 5.2 squared plus 6 squared is equal to h squared. Now I'm going to figure this all out on my calculator, all right? I'm just going to take my calculator out. And I mean, normally I'd figure out what they are individually, but there's really no reason to do that. I'm going to do 5.2 squared plus 6 squared. That's going to give me 63.04. And my height now is the square root of 63.04. So let me figure out what that is. Should be just a little bit less than 8, I think. Yep. So let me say 7.94, maybe round it to 2 decimal places. That's what that particular height's going to be in inches. And now I have everything I need to figure out the area of one of those triangular faces. The base is 12 inches. The height is 7.94 inches. So I can now say, give myself a little bit of extra room, The area of one of those faces is 1/2 its base times its height. And what do I want to the nearest 1/10 of a square inch? So let me bring this up a little bit further. 1/2 times 12 times 7.94. It's probably the only time we'll deal with area in this lesson, and that is 47.6. I almost put down cubic or square centimeters again. 47.6 square inches. All right, and that is it. Okay, so let's go on and let's take a look at another modeling problem. Here we go. Exercise number 2. A hoop house is a type of greenhouse. It is made by stretching plastic over identical semicircles. A hoop house whose diameter is 14 feet, height is 8 feet, and length is 25 feet is shown below. Letter A. What would be an appropriate solid to model the hoop house with? So this is always the first question we have to ask, right? What of our sort of like tool bag of solids can we use to model whatever shape we're working with? Pause the video now and tell me what you see. All right, well, I'm going to say a half cylinder. I wonder if semi-cylinder is correct. I don't know, I've never heard that term. I'm going to call it a half cylinder. Right? That's what we've got, a half cylinder. All right, the other half would be kind of down here. Okay? Now, honestly, it doesn't particularly matter what we call it, right? We should be able to find the volume because we have a constant cross-section all the way through this thing. You can literally see, right, the hoops themselves are these identical semicircles. And that leads us to letter B. Find the volume of the hoop house to the nearest cubic foot. All right, see if you can figure out the volume of the hoop house. Well, keep in mind, right, that the volume of anything that has a constant cross-sectional area will be the area of that particular face times the depth, right? So I just need to figure out the area of that semicircle, and then I need to multiply it by the depth. In fact, right, the volume, first the area of the semicircle. Since a semicircle, it's going to have 1/2 pi r squared times h. That's really going to be our volume formula, in which case we'll have 1/2 times pi. Our radius here is 7 squared, and then our h, which isn't really a height anymore, it's actually a depth, is 25, right? So you really have to take that h kind of in stride, right? This is like a cylinder lying on its side, so the h really isn't a height so much as it is a depth. All right, now it's just about cranking this into our calculator as usual. Let me clear that out. We need to throw that 1/2 in there because it's only half of a semicircle, or half of a cylinder. 1/2 times pi times 7 squared times 25. And that will give us, to the nearest cubic foot, a volume of 1,924 cubic feet. All right, 1,924 cubic feet. That's a pretty big volume, you know, or at least it feels like it's a pretty big volume. Now, oftentimes when you have greenhouses, right, to prevent things like mold, mildew, and things like that, you need to move a lot of air through them. That's why when you go into a greenhouse, they'll tend to be huge fans that are always blowing. Let's take a look at a little bit of a design problem that has to do with that. Letter C. Farmers would like to replace the entire volume of air in this hoop house 8 times each hour. They can buy a fan that moves air at 200 cubic feet per minute, 300 cubic feet per minute, or 400 cubic feet per minute, with the higher capacity fans costing more. Which fan should they purchase? Explain. All right, well, I'd like you to pause the video right now, right, and using just things like the volume that you know, the fact that you've got to move that volume 8 times each hour, right, and the fact that there's 60 minutes in an hour, right, I want you to use all of that to make a judgment call on which of these 3 fan sizes you would suggest to do the job that they're looking to do? All right, well, the first thing I'd like to know is just how much volume of air I need to move in an hour, right? This is how much volume is in the hoop house, but I'm going to move it 8 times each hour. So I'm going to say the volume moved must be 1,924 times 8, right? This is how much I got to move in an hour. So let's take 1,924, still not. Oh, it happened again. 1,924 times 8, that gives me 15,392 cubic feet that I need to move per hour. And if we had fans that were rated on a per hour basis, well, then we would make the judgment call based on this number. But most of the time, fans are rated in terms of what volume they can move per minute, all right? So it's easy enough, right? We can now say that our rate is going to be 15,392 cubic feet per 60 minutes, and that is going to be easy enough. Divide by 60. Ah, of course not. And still not. Let's try 15 and again. And again. All right, let's move this, see if that works better. 15,392 divided by 60. And now instead of getting a fraction, I want a decimal. There it is. Technology. 256.53 cubic feet per minute. All right, so I've got to move 256 or 257 cubic feet of air each minute in order to move all of this volume 8 times each hour. So I'm going to go with the 300 cubic foot per minute fan. The 200 cubic foot per minute fan isn't going to be high enough, and the 400 cubic fan per minute is going to be more than enough, but it's going to cost more than I need to spend, right? So the suggestion is the 300 cubic foot per minute fan. That's the one that we want. All right, and that's that. Let's take a look at one last problem. All right, exercise number 3. Dry sand is poured into a pile that has a diameter of 8 meters. The pile has horizontal cross sections that are circular, and sides of the pile all slope upward at a constant angle of 34 degrees. Letter A, what would be an appropriate solid to model the sand pile with? All right, well, as always, we start with this question: what solid should I be using? Pause the video now and go ahead and answer that question. All right, well, it should be a cone, right? So a cone is a shape that basically looks like a triangle, right, from a side, and that's because you can revolve a right triangle or rotate a right triangle around one of its legs to create the cone, and it's got cross sections, horizontal cross sections that are circular. So this is most certainly going to be modeled with a cone and not a pyramid, okay? And that's key, right? It's not going to be a pyramid because its cross sections are circular. And that kind of makes sense. If you've ever seen like a rock pile or a sand pile or anything that came from just pouring the rock or the sand out, it pretty much always falls in the shape of a cone. Now, if we're going to eventually figure out what the volume of this cone is, one of the big pieces there is the height of the cone. And let's take a look at that in letter B. Determine the height of the sand pile to the nearest hundredth of a meter. Okay, well, what do we know, right? You know, we know that the sand pile slopes up at 34 degrees. We know it's 8 meters across. Pause the video now and see if you can figure out a way to calculate the height of the sand pile. Well, keep in mind, if we sliced the sand pile right through the vertex, right through the part where we would have a height, here's what we would see. We would see something that would look like this. And it would be 8 meters like this, it would be 34 degrees here, 34 degrees here, and we want to know that distance, right? So what are we going to do? We're going to use right triangle trigonometry, okay? And specifically, I'm going to take that isosceles triangle, break it in half like that. That's now going to be 4 meters. I'll call that h, the height. This is going to be 34 degrees. Now I've got the side that's adjacent to the 34 degrees. I'm looking for the opposite side. Opposite and adjacent is the tangent ratio. So I can say that the tangent of 34 degrees is equal to h divided by 4, and h will be 4 times the tangent of 34. So let's now figure out what the height of my sand pile is. 4 times trig, tangent of 34. Been a little while since we've used the tangent, and that's h equals 2.698, so that's 2.70 meters. Now, by the way, you might think the nearest hundredth of a meter is rounding to really fine precision. Don't forget the hundredth of a meter is a centimeter. So we're really talking about a height of 270 centimeters, right? All right, let's take a look at letter C. Determine the volume of the sand pile to the nearest tenth of a cubic meter. Well, right, see if you can remember what the volume of a cone is, and then use that to figure out the volume of the sand pile. All right, well, the volume of a cone is 1/3 the volume of the cylinder that it would sit inside of that has the same height. So the volume of a cone is 1/3 pi r squared h. In this case, that's going to be 1/3 times pi times the radius, whoops, which is not 8, it's 4. I almost used 4, times 4 squared times that height that we just figured out. So the volume of this cone, 1/3 pi times 4 squared times 2.70. All right, let's figure that out. Maybe bring this up a little bit further. Here we go. Oh man, 1/3 pi times 4 squared times 2.70. All of that will give me my volume as 45.2 cubic meters. Actually, quite a large volume. 45.2 cubic meters. It's a large sand pile. 8 meters across, right? 8 meters across, that's like about 24 feet across. That's a big sand pile. Let's take a look at letter D. If the total weight of sand in the pile is 72,500 kilograms, what is the density of the sand? Round to the nearest whole number and include units. All right, why don't you pause the video and go ahead and do that. All right, well, density, right, whether it's a weight or a mass or whatever, density is going to be how much of that fits inside of that. So it's really quite easy, right? The density of the sand is going to be 72,500 kilograms divided by 45.2 cubic meters. Well, let's take a look at what that is. 72,500 divided by 45.2 gives me a density of 1,604 kilograms per cubic meter. And that's the density of the sand, right? And that's a very realistic density of sand. Pretty sure it would actually sink if we threw it into water. All right, let's wrap this up. So geometric modeling, right, is almost the pinnacle of your work in this unit, right? The idea that we can look out at the world and look at three-dimensional objects in the world and either have an exact three-dimensional shape that we've worked with that can model that, or an approximate shape. And I would say the sand pile is a good example of an approximate shape. Probably most sand piles and, rock piles and things like that are conical, but not a perfect cone or anything like that, right? Whereas the hoop house was probably well approximated with a half cylinder, and that first problem with the monument, certainly, right? A prism and a pyramid were pretty much exactly what we had to use in that situation. So geometric modeling, sometimes you're using approximate shapes, sometimes you're using exact shapes, but regardless, we do this all the time in all sorts of different contexts within engineering, manufacturing, medicine, all sorts of different areas where you have to use geometric shapes that we've been working with to model a particular phenomenon. All right, well, this was our last lesson in our geometry course, a course that has run the gamut from looking at geometric proof, both in the Euclidean plane and the coordinate geometry plane. We've looked at right triangle trigonometry that we've used for all sorts of different things. We've looked at dilations, being able to stretch and shrink objects. And then, of course, in this last unit, we've also looked a lot at three-dimensional objects and how to find their volume and model with it. Geometry is a beautiful subject that really ranges all over the place, and I wish you almost had to take a second course of it in high school. And I encourage you to look more at geometry as you move on in mathematics. And of course, I hope you continue in mathematics past geometry. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. Until I see you again in Algebra 2, keep thinking and keep solving problems.